An ionic liquid is a salt in the liquid state. In some contexts, the term has been restricted to salts whose melting point is below some arbitrary temperature, such as 100 °C. While ordinary liquids such as water and gasoline are predominantly made of electrically neutral molecules, ionic liquids are largely made of ions and short-lived ion pairs. These substances are variously called liquid electrolytes, ionic melts, ionic fluids, fused salts, liquid salts, or ionic glasses. Ionic liquids have many applications, such as powerful solvents and electrically conducting fluids. Salts that are liquid at near ambient temperature are important for electric battery applications, and have been used as sealants due to their very low vapor pressure. Any salt that melts without decomposing or vaporizing usually yields an ionic liquid. Sodium chloride, for example, melts at 801 °C into a liquid that consists largely of sodium cations and chloride anions. Conversely, when an ionic liquid is cooled, it often forms an ionic solid or which may be either crystalline or glassy. The ionic bond is usually stronger than the van der Waals forces between the molecules of ordinary liquids. For that reason, common salts tend to melt at higher temperatures than other solid molecules. Some salts are liquid at or below room temperature. Examples include compounds based on the 1-ethyl-3-methylamidazolium cation and include EMIMCl, EMIM dicyanamide, C, 2 hours, 5, CH, 3, C, 3 hours, 3N+, 2N, CN, 2, that melts at a 21 °C. And 1-butyl 3,5-dimethylpyridinium bromide which becomes a glass below a 24 °C. Low-temperature ionic liquids can be compared to ionic solutions, liquids that contain both ions and neutral molecules, and in particular to the so-called deep eutectic solvents, mixtures of ionic and non-ionic solid substances which have much lower melting points than the pure compounds. Certain mixtures of nitrate salts can have melting points below 100 °C. The term ionic liquid in the general sense was used as early as 1943. History: the discovery date of the first ionic liquid is disputed, along with the identity of its discoverer. Ethanol ammonium nitrate was reported in 1888 by S. Gabriel and J. Weiner. One of the earliest truly room-temperature ionic liquids was ethyl ammonium nitrate, C, 2 hours, 5, NH+, 3NO, 3, synthesized in 1914 by Paul Walden. In the 1970s and 1980s ionic liquids based on alkyl-substituted imidazolium and pyridinium cations, with halide or tetrahalogenaluminate anions, were initially developed for use as electrolytes in battery applications. An important property of the imidazolium halogenaluminate salts is that their physical properties such as viscosity, melting point, and acidity could be adjusted by changing the alkyl substituents and the imidazolium pyridinium and halide halogenaluminate ratios. Two major drawbacks for some applications were moisture sensitivity and acidity basicity. In 1992, Wilkes and Zawarutka obtained ionic liquids with neutral weakly coordinating anions such as hexafluorophosphate, Fe, 6, and tetrafluoroborate, BFA, 4, allowing a much wider range of applications. Recently a new class of AERA and Mosuria stable, neutral ionic liquids became available. Research has also been moving away from hexafluorophosphate and tetrafluoroborate towards less toxic alternatives such as bistriflamide, CF, 3SO, 2, 2N, or away from halogenated compounds completely. Moves towards less toxic cations have also been growing, with compounds like ammonium salts proving to be as flexible a scaffold as imidazolium. Characteristics: ionic liquids are often moderate to poor conductors of electricity, non-ionizing, highly viscous and frequently exhibit low vapor pressure. Their other properties are diverse, many have low combustibility, excellent thermal stability, wide liquid regions, and favorable solvating properties for a range of polar and nonpolar compounds. Many classes of chemical reactions, such as Diels-Alder reactions and Friedel-Crafts reactions, can be performed using ionic liquids as solvents. Recent work has shown that ionic liquids can serve as solvents for biocatalysis. The miscibility of ionic liquids with water or organic solvents varies with side chain lengths on the cation and with choice of anion. They can be functionalized to act as acids, bases or ligands, and have been used as precursor salts in the preparation of stable carbons. Because of their distinctive properties, ionic liquids are attracting increasing attention in many fields, including organic chemistry, electrochemistry, catalysis, physical chemistry, and engineering. See for instance magnetic ionic liquid. Despite their extremely low vapor pressures, some ionic liquids can be distilled under vacuum conditions at temperatures near 300 degrees Celsius. In the original work by Martin Earle, al., the authors wrongly concluded that the vapor was made up of individual, separated ions, but was later proven that the vapors formed consisted of ion pairs. Some ionic liquids generate flammable gases on thermal decomposition. Thermal stability and melting point depend on the liquid's components. Thermal stability of various RTILs are available. The thermal stability of a task-specific ionic liquid, protonated butane bis, trifluoromethanesulfonyl, imide is of about 534 K and N-butyl N-methylpyrrolidinium bis, trifluoromethanesulfonyl, imide was thermally stable up to 640 K. The upper limits of thermal stability of ionic liquids reported in the literature are usually based upon fast TGA scans, and they do not imply long-term thermal stability of ionic liquids, which is limited to less than 500 K for most ionic liquids. The solubility of different species in imidazolium ionic liquids depends mainly on polarity and hydrogen bonding ability. Saturated aliphatic compounds are generally only sparingly soluble in ionic liquids, whereas olefins show somewhat greater solubility, and aldehydes can be completely miscible. This can be exploited in biphasic catalysis, such as hydrogenation and hydrocarbonylation processes, allowing for relatively easy separation of products and/or unreacted substrate, S. Gas solubility follows the same trend, with carbon dioxide gas showing exceptional solubility in many ionic liquids. Carbon monoxide is less soluble in ionic liquids than in many popular organic solvents, and hydrogen is only slightly soluble and may vary relatively little between the more commonly used ionic liquids. Different analytical techniques have yielded somewhat different absolute solubility values. Room temperature varieties. Room temperature ionic liquids consist of bulky and asymmetric organic cations such as 1-alkyl-3-methylimidazolium, 1-alkyl-pyridinium, N-methyl-N-alkyl-pyrrolidinium and ammonium ions. Phosphonium cations are less common, but offer some advantageous properties. A wide range of anions are employed, ranging from simple halides, which generally suffer high melting points, to inorganic anions such as tetrafluoroborate and hexafluorophosphate, and to large organic anions like bistriflamide, triflate or tosylate. There are also many interesting uses of ionic liquids with simple non-halogenated organic anions such as formate, alkyl sulfate, alkyl phosphate or glycolate. The melting point of 1-butyl-3-methylimidazolium tetrafluoroborate with an imidazole skeleton is about 80 degrees Celsius and it is a colorless liquid with high viscosity at room temperature. If a highly asymmetric cation is combined with a highly asymmetric anion, formed ionic liquid may not freeze down to very low temperatures and the glass transition temperature was detected below -100 degrees Celsius in the case of ionic liquids with N-methyl-N-alkyl-pyrrolidinium cations and fluorosulfonyl trifluoromethanesulfonylimide. In many synthetic processes using transition metal catalysts, metal nanoparticles play an important role as the actual catalyst or as a catalyst reservoir. ILs are an appealing medium for the formation and stabilization of catalytically active transition metal nanoparticles. More importantly, ILs can be made that incorporate coordinating groups, for example, with nitrile groups on either the cation or anion. In various CC coupling reactions catalyzed by a palladium catalyst, It has been found that palladium nanoparticles are better stabilized in CNIL compared to non-functionalized ionic liquids. Thus enhanced catalytic activity and recyclability are realized. Low-temperature varieties. Low-temperature ionic liquids have been proposed as the fluid base for an extremely large diameter spinning liquid mirror telescope to be based on the Earth's moon. Low temperature is advantageous in imaging long-wave infrared light, which is the form of light that arrives from the most distant parts of the visible universe. Such a liquid base would be covered by a thin metallic film that forms the reflective surface. Low volatility is important for use in lunar vacuum conditions. Applications. ILs find a variety of industrial applications. A few industrial applications are described below. More detailed information can be found in a recent review article. Chemical industry. The first major industrial IL application was the Basel process by BASF, in which 1-alkylamidazole scavenged the acid from an existing process. This then results in the formation of an IL which can easily be removed from the reaction mixture. This increased the space-time yield of the reaction by a factor of 80,000. Eastman operated an IL-based plant for the synthesis of 2,5-dihydrofuran from 1996 to 2004. The dimersal process is a traditional way to dimerize short-chain alkanes into branched alkanes of higher molecular weight. Y. Chauvin and H. Olivier Berbiger developed an IL-based add-on to this process called the dimersal process. Ionic ylation is an ILA-Euro-based process developed by PetroChina for the alkylation of 4-carbonolefins with isobutane. Their 65,000-ton per year plant is claimed to be the biggest industrial application of ionic liquids to date. Pharmaceuticals. Recognizing that approximately 50% of commercial pharmaceuticals are organic salts, ionic liquid forms of a number of pharmaceuticals have been investigated. Combining a pharmaceutically active cation with a pharmaceutically active anion leads to a dual-active ionic liquid in which the actions of two drugs are combined. Cellulose processing. At a volume of some 700 billion tons, cellulose is the Earth-Euro-unregistered trademark's most widespread natural organic polymer and thus highly important as a renewable resource. But even out of nature's annual 40 billion tons output, only approximately 5% is used as feedstock for further processing. More intensive exploitation of cellulose, as a renewable feedstock, is aided by the development of suitable solvents for mechanical and chemical processing. ILs have been shown to be highly effective at solvating cellulose to technically useful concentrations. This may allow for development of new processes and intensification of existing ones, substituting existing cellulose solvents with ILs. The use of molten salts in cellulose processing originally dates back to a patent application from 1930 where mixtures of molten 1-alkylpridinium chlorides were used to dissolve cellulose, followed by subsequent chemical and mechanical processing. Further advances have generally led to lowering of melting points and viscosities to a point where there are now room temperature ionic liquids available that dissolve cellulose. There are also examples of in situ cellulose valorization in ionic liquids into various valuable chemicals, for example glucose esters, sorbitol, and alkyl glycosides. Such techniques create new opportunities for fine chemicals production and can be, of course, useful for commercial applications. Making viscose-based fibers from dissolving pulp currently involves the use, and subsequent disposal, of great volumes of various chemical auxiliaries, ESP carbon disulfide, CS2. Major volumes of wastewater need to be disposed of. Following in the footsteps of the lyocell process, which uses hydrated N-methylmorpholine N-oxide, as a novel non-aqueous solvent for the dissolution of the pulp, it has been suggested that IL can greatly simplify these processes, serving as solvents that are potentially recyclable. The A-Euro-OE Institut für 1/4 Textilchemie Euro and Dean Kendorf and BASF are jointly investigating the properties of fibers spun from solutions of cellulose dissolved in IL in a pilot plant. The dissolution of cellulose-Euro-based materials like tissue paper waste, generated in chemical industries and at research laboratories, in room temperature IL-1-butyl-3-methylamidazolium chloride, BMIMCL in the recovery of valuable compounds by electrode position from this cellulose matrix was studied. Fundamental research, IELs can be used as model systems for electrode-electrolyte interfaces in ultra-high vacuum systems. Algae processing. Algae are perhaps the most widespread organisms on Earth, occupying most niches on the planet. Algae perform photosynthesis and produce high-energy molecules such as lipids and sugars, that can be converted to useful chemicals such as biodiesel, ethanol and other biofuels. To accomplish this, however, algae must be harvested and their constituents extracted from within the cells in an economically viable industrial process. IELs have been shown to be effective at destroying the cell wall and releasing cell contents using a fraction of the energy, and potentially the cost, of current harvesting and extraction processes. Dispersants. IELs can act as dispersing agents in paints to enhance finish, appearance and drying properties. IELs are used for dispersing nanomaterials at IELIC. Gas handling. IELs have several properties that make them useful in gas storage and handling applications, including low vapor pressure, stability at high temperatures, and solvation for a wide variety of compounds and gases. They also have weakly coordinating anions and cations which are able to stabilize polar transition states. Many ionic liquids can be reused with minimal loss of activity. The company Air Products uses IELs instead of pressurized cylinders as a transport medium for reactive gases such as trifluorobron, phosphine and arsine. The gases are dissolved in the liquids at or below atmospheric pressure and are easily withdrawn from the containers by applying a vacuum. Gas manufacturer Linde exploits the low solubility of hydrogen in IELs to compress the gas up to 450 bar in filling stations by using an ionic liquid piston compressor, which has only 8 moving parts. IL-1-butyl-3-methylamidazolium chloride has been used for separating hydrogen from ammonia boron. IELs and amines can be used to capture carbon dioxide CO2 and purify natural gas. Nuclear fuel reprocessing. IL-1-butyl-3-methylamidazolium chloride has been investigated as a non-aqueous electrolyte media for the recovery of uranium and other metals from spent nuclear fuel and other sources. Protonated butane bis, trifluoromethanesulfonyl, imide has been investigated as a solvent for uranium oxides. Ionic liquids, N-butyl-N-methylpyrrolidinium bis, trifluoromethylsulfonyl, imide and N-methyl N-propylpiperidinium bis, trifluoromethylsulfonyl, imide, have been investigated for the electrode position of europium and uranium metals respectively. Solar thermal energy. IELs have potential as a heat transfer and storage medium in solar thermal energy systems. Concentrating solar thermal facilities such as parabolic troughs and solar power towers focus the sun's energy onto a receiver which can generate temperatures of around 600 degrees Celsius. This heat can then generate electricity in a steam or other cycle. For buffering during cloudy periods or to enable generation overnight, energy can be stored by heating an intermediate fluid. Although nitrate salts have been the medium of choice since the early 1980s, they freeze at 220 degrees Celsius and thus require heating to prevent solidification. Ionic liquids such as CMIM, 4, BF, 4, have more favorable liquid phase temperature ranges and could therefore be excellent liquid thermal storage media and heat transfer fluids. Food and bioproducts. IL-1-butyl-3-methylamidazolium chloride completely dissolves freeze-dried banana pulp and with an additional 15% DMSO, lends itself to carbon-13 NMR analysis. In this way the entire banana complex of starch, sucrose, glucose, and fructose can be monitored as a function of banana ripening. IELs can extract specific compounds from plants for pharmaceutical, nutritional and cosmetic applications, such as the anti-malarial drug artemisinin from the plant Artemisia annua. Waste recycling. IELs can aid the recycling of synthetic goods, plastics and metals. They offer the specificity required to separate similar compounds from each other, such as separating polymers in plastic waste streams. This has been achieved using lower temperature extraction processes than current approaches and could help avoid incinerating plastics or dumping them in landfill. Batteries. Researchers have identified ILs that can replace water as the electrolyte in metal-air batteries. ILs have great appeal because they evaporate at much lower rates than water, increasing battery life by drying slower. Further, ILs have an electrochemical window of up to 6 volts, supporting more energy-dense metals. Energy densities from 900 to 1600 watt-hours per kilogram appear possible. A metal-air battery draws oxygen through a porous ambient air electrode and produces water, hydrogen peroxide, or hydroxide anions depending on the nature, oxygen reduction catalyst and electrolyte. These compounds store the electrons released by the oxidation of the anode. Safety: Ionic Liquids' low volatility effectively eliminates a major pathway for environmental release and contamination. However, this property is distinct from toxicity. Ionic Liquids' aquatic toxicity is as severe as or more so than many current solvents. Mortality isn't necessarily the most important metric for measuring impacts in aquatic environments, as sublethal concentrations change organisms' life histories in meaningful ways. Balancing VOC reductions against waterway spills requires further research. Ionic Liquids' substituent diversity simplify the process of identifying compounds that meet safety requirements. Ultrasound can degrade solutions of imidazolium-based ionic liquids with hydrogen peroxide and acetic acid to relatively innocuous compounds. Despite low vapor pressure, many ionic liquids are combustible and therefore require careful handling. Brief exposure to a flame torch can ignite some ionic liquids. Complete combustion is possible for some ionic liquids. See also, MDYNA mix software for ionic liquids simulations, 1-butyl-3-methylimidazolium hexafluorophosphate for an often encountered ionic liquid, trioctyl-methylammonium bis, trifluoromethylsulfonyl, imide, Aza-Bieliza-Euro-Hillman reaction for the use of a chiral ionic liquid in asymmetric synthesis. References. Further reading, Thomas Welton. Room temperature ionic liquids. Chem. Rev 99, 2071 Euro 2084. doi, 10.1021/CA980032 TIA, Effenders, SZ and Al-Abedin. Air and water stable ionic liquids in physical chemistry. Phys. Chem. Chem. Phys 8, 2101 Euro 16. Bibcode, 2006 PCCP, 8.2101 EDOI, 10.1039/P600519P. PMIDA 16751868 Niazi Bikuk. A new ionic liquid, 2-hydroxyethylammonium formate. Journal of Molecular Liquids 116, 15 Euro 18 doi, 10.1016/J Molick. 2004.03.006 S. Fujita, H. Kanemaru, H. Senboku and MRI. Preparation of cyclic urethanes from amino alcohols and carbon dioxide using ionic liquid catalysts with alkali metal promoters. Int. J. Molsci 2006, 438 Euro 450 doi, 10.3390/I710043 Freemantle, Michael. An Introduction to Ionic Liquids. Royal Society of Chemistry. ISBN A978-1-84755-161-0. External links, Ionic Liquids Biological Effects Database, free database on toxicology and cotoxicology of ionic liquids, corresponding states for ionic fluids. Applications, such as powerful solvents and electrically conducting fluids. Salts that are liquid at near ambient temperature are important for electric battery applications, and have been used as sealants due to their very low vapor pressure. Any salt that melts without decomposing or vaporizing usually yields an ionic liquid. Sodium chloride, for example, melts at 801 AA degrees Celsius into a liquid that consists largely of sodium cations and chloride anions. Conversely, when an ionic liquid is cooled, it often forms an ionic solid or euro, which may be either crystalline or glassy. The ionic bond is usually stronger than the van der Waals forces between the molecules of ordinary liquids. For that reason, common salts tend to melt at higher temperatures than other solid molecules. Some salts are liquid at or below room temperature. Examples include compounds based on the 1-ethyl-3-methylamidazolium cation and include EMIMCl, EMIM dicyanamide, C, 2 hours, 5, CH, 3, C, 3 hours, 3N+, 2N, CN, 2, that melts at a 21 AA degree Celsius. And 1-butyl 3,5-dimethylpridinium bromide which becomes a glass below a 24 AA degree Celsius. Low-temperature ionic liquids can be compared to ionic solutions, liquids that contain both ions and neutral molecules, and in particular to the so-called deep eutectic solvents, mixtures of ionic and non-ionic solid substances which have much lower melting points than the pure compounds. Certain mixtures of nitrate salts can have melting points below 100 degrees. An ionic liquid is a salt in the liquid state. In some contexts, the term has been restricted to salts whose melting point is below some arbitrary temperature, such as 100 AA degree Celsius. While ordinary liquids such as water and gasoline are predominantly made of electrically neutral molecules, ionic liquids are largely made of ions and short-lived ion pairs. These substances are variously called liquid electrolytes, ionic melts, ionic fluids, fused salts, liquid salts, or ionic glasses. Ionic liquids have many uses. The term ionic liquid in the general sense was used as early as 1943. History: the discovery date of the first ionic liquid is disputed, along with the identity of its discoverer. Ethanol ammonium nitrate was reported in 1888 by S. Gabriel and J. Weiner. One of the earliest truly room-temperature ionic liquids was ethyl ammonium nitrate, C, 2 hours, 5, NH+, 3NO, 3, synthesized in 1914 by Paul Walden. In the 1970s and 1980s ionic liquids